Hello. Should I zoom in? Yeah, that's me. Cool. Hello. Thank you, Wei, for um, basically telling or saying that we'll be having a PyBullet session. That's correct. Cool. So let's just wait probably 2 more minutes, 1 more minute. Let's build a robot, okay? Let me just change the banner to. Do I have to ask me anything, banner from Wei, that I can use? Did he? Let's see. Check in. Nope, nope, nope. Well, that's bad. Okay. I'll create a banner that says, "Ask me anything." Let's learn together. Happy face? No happy face. Cool. Add banner. And then scroll across. Yeah, there we go. I think that was better. Cool. Okay, so just let me know if either music is too low or too loud, or my voice is either too low or too loud. Okay. Should be good. Just let me know. Okay. Cool. Me neither. Let's see. Let's do it. First of all, let me just share with you the link to register. Okay. Yeah, there it is. Okay, cool. So, let's start. Do okay. So you can see it's not a very mathematical presentation. It's an easy presentation. Okay. For whoever said want to build a robot, yes, but no. Okay, so building a robot is. I was going to do one of those. You have to understand a lot of calculus to be able to move it, okay? Because when you build a robot, you have to create a map of points, okay? And there are singularities in there. It's a lot of math. So yeah, it took me like 3 months to learn it when I was studying. I don't think I'll show it in a stream. We could do it. We could try it. We'll build some robots, but not entirely. Okay. Cool. A little bit of an intro about myself. My name is Charo. People call me Bully. You can call me by name or nickname. Um, I'm 24. I'm turning 24 in 3 days. Um, I am a robotics and telecommunications engineer, so I work with robots. The robots that I like the most are drones. I think drones are really interesting. The fact that they get to fly, that's cool. I would like to work with boats. Okay, like either boats or drones that can go underwater. That's cool. Um, but yeah, do I like autonomous vehicles and all of that? I like them. It's not my go-to, but I like them. It's cool. It's just I don't know. If you give me to choose between something that flies or something that just rolls in the ground, I'd like something that flies. Cool. Okay. So awesome. Cool. Let's see. So let's go into what's PyBullet. Okay. Um, just FYI, okay? FYI, I didn't know that PyBullet existed. Hello from Qatar. That's really cool. Happy birthday. Thanks so much. Want to go to Qatar someday. I speak Arabic, so I would definitely like to go to Qatar someday. Cool. Okay. I wasn't going to do a PyBullet one, okay? Um, I was going to do a ROS, which is a robotics operating system one. I just updated my Ubuntu to 24 LTS, I think it was. It doesn't work. ROS doesn't work in Ubuntu 24 LTS. So, was it 24? 26 LTS, the latest one, okay? It doesn't work. So, I was like, I want to do something about robots. Let's try PyBullet. Read about it. I'm learning how to use it. So, probably some questions we'll answer them together, okay? But yeah. Just that FYI, okay? Cool. So intro to PyBullet. So what's PyBullet? Okay. So usually engineers or people that are working with robots, specifically with robots, we do not work with the real thing up until we have something that works. Okay? Why is that? Because it's way cheaper to break something in a simulator than a real robot. Okay? It's as easy as it sounds. Okay, you can control everything in a simulation. You can control, I don't know, if you're training a robot with reinforcement learning, you can train 100 robots at the same time, and they're learning with a swarm. Okay, that doesn't happen in real life. Okay, if you want to try something out, it's basically cheaper to try it here if you don't have the actual robot. And then you can see if it works, then you can invest in a robot or buy it or rent it. I don't know. That's what simulators are for, and that's why they're really important, because there's some robots that are not cheap. Okay, if you wanna use a drone, it's probably not that cheap. But for example, this Boston Dynamics dog, it's I don't know if it's like 2-3 million pesos. Okay, so it's like $150,000 or more. Okay, so they're not cheap. Okay, lidars, for example, there are some sensors that turn and send light signals and can see their surroundings, which will work with one. Those are not cheap either. Okay, if you break one of those, being happy is the last thing that you'll be. Okay, so that's why we use simulators. PyBullet is a simulator, open source, that was developed by Meta, okay, by Facebook AI, and it's pretty popular as I've seen. You can use Python with it, okay, so it's easy to use. You have to understand some mathematical things, okay, but that's fine. We'll go into those things, okay. Cool. You can see that we have some Boston Dynamics robot here. We have a car with a lidar here. You can see that's the signal. We have some arms, two-legged robots, and we have the four-legged ones. It all depends on your needs that you can import robots. Okay. You can see here. I'll probably zoom. Oh, I won't zoom. You can see here each joint is of a different color. It's because each joint is a different piece. Okay, these are called URDFs. Okay, URDFs are okay, the real meaning is user defined user. Okay, what's a URDF? What was the meaning of URDF? URDF. I forgot the name. Unified Robot Description Format. Okay, so basically you can describe robots with shapes using URDF. You paste them together, and it's basically you don't see them like this. It's like a square with another square, and the fact that you get to see them like with the shape, it's because you can paste an image over it, and that's why you can see robots like this. Okay, it's not that each piece is a single part. The URDF it's basically a blocks. Okay, like a hitbox in a game. Okay, it's just a box. Okay, cool. Okay, so for reference, okay, when you're working with robots, because some other people that work with math do it the opposite way. Okay, so you do this. Okay, so do like this. So your thumb is going to be the Z coordinate. Your index is going to be the X coordinate, and the middle finger is going to be the Y coordinate. Okay, so when you work with robots, you have to always have this memorized. Okay, it's not that your thumb is Y and your middle finger is Z. Many people do that, not for robots. Okay, for robots, Z is always the upper axis. Okay, so if a robot spins on its axis, it's because it's rotating in Z. Okay, and you can see here we have some names. We have roll, which is in the X, pitch, which is in the Y, and yaw, which is in the Z. Okay, so it means if that plane is going to turn, then it'll use the roll axis, right? Like it kind of rolls a little bit and it turns. Okay, have you seen planes roll a bit and they turn? That's how they do it. A plane usually doesn't use the yaw axis to turn. Even though it turns in the yaw axis, it doesn't just do like this, like a drone. Okay, it cannot do it. Okay, it just rolls a bit, and using the X, it turns in Z. Okay, the planes don't use the pitch axis. It'll, I don't know, it doesn't make sense. It would go like that. Okay, so each robot has its own axis of turning. Okay, now we'll go back to this. Okay, but we have something also called degrees of freedom. Okay, so we'll work with some robots, some robotic arms. Okay, you can see that each joint, this robot, I think it's a KUKA. Is it a KUKA? I'm not sure. I think it's a KUKA. Okay. Each joint has its own axis. Okay. So for example, the first joint, you can see it's actually in the Z axis that it turns. Okay. It means that it's yawing. Okay. Now, the second joint, if we keep that nomenclature, it's turning in our X axis, which is rolling. Okay. Each joint represents a degree of freedom. Okay, it means the more joints you have, the more degrees of freedom you have. That said, the more mathematical calculations you have to do for this robot to reach a certain point. Okay, so it's not like I want to add like 10 joints. Like you can do it. First of all, it's not cheap. It's very expensive. You'll use way more power. You have to control a lot of things, and it's probably very redundant. Okay, some of the joints are redundant by default because of security. Okay, these robots can carry a car. They usually carry cars from point A to point B. You don't want that car falling. Okay, these robots are really expensive. Okay, you can use them in the simulator. That's why we simulate. Okay, cool. Now, you can see that this one has 6 joints, meaning 6 degrees of freedom. Okay, you need one of those. You're talking about the Da Vinci. So, Da Vinci's are humanoid-like robots that are controlled by the doctors, interestingly enough, the doctor has to move like it has to exaggerate their movements for the Da Vinci to move precisely. Okay, but yeah, it's one of those. Okay, but you know, Da Vinci is just way more sophisticated than something like this. Okay, but yeah, I hope knee surgery goes well. You can see that this thing is called I think it's a waffle pie. It's a car. It doesn't have degrees of freedom. Okay, it's just moves in the z-axis. It turns. That's what it does. It doesn't have a degree of freedom because it cannot just turn in the z. I'm sorry, it cannot turn in the y. Okay, so in the should be the pitch. It doesn't pitch. Okay, cool. Yeah, easy. Okay, we'll get to that. Okay, so those are degrees of freedom. Okay, hey Tammy, awesome. Okay, so let's see. Let's do this now. Very easy things. Okay. Open Visual Studio Code. You can see I have here my templates, but I won't use them there. I'll use my iPad. I'll just open here stream codes, and probably I'll do PyBullet 1.py. As simple as that. Okay. So we need a Python environment. Okay. How do you do that? You open your terminal. Okay. Can you see the terminal correct? Okay. Should I zoom in? There we go. Maybe. In Windows. Okay. On Windows, you do py-m venv, and then the name of the virtual environment. I always use env. It's just, I don't know. It's for me, it's the convention. Okay. So py-m venv env, enter, and it'll create the virtual environment with Python. Okay. Cool. Now, why should you use a venv? You don't want to download libraries that you're not going to use in your root Python. Okay, what it does, it kind of creates like a copy of your Python, and it's like a sticker, so it pastes over your Python, and you can either use it or deactivate it and not use it, but it's not in your native Python. Okay, so if there's an error or some libraries don't go well with each other, then the problem is in your venv, not your native Python. Okay, cool. So that's what you do it. And then on Windows, I think if you're on Mac, you have to do, or Ubuntu, you have to do Python 3-m venv env in my case. Okay, this is for Mac. Okay, if you have a Windows, do the Py. Okay, cool. Now, yeah. I mean, Conda is still in a, like, it's contained in a folder, in the Conda folder, so you have to look for it. I feel like venv gives you more, how can I say this? Like more control, but it doesn't give you that much control over your GPU. Okay, so for example, in my case, I do have an NVIDIA GPU. I have trained some models, and my 1, 2, 3. So on Wednesday, I'll have a stream about YOLO and Deep Sword. Okay, we're going to use a Conda env. We can use a pip env. It just goes way too slow. Okay, because it doesn't really connect GPU that well as Conda does. Okay, but yeah, venv with Conda is different. Okay, cool. You can use pip with Conda. It works. I guess that's the good thing about Conda. You can use pip inside of Conda, but not Conda inside of pip. C'est la vie. Cool. Okay, so we have to activate it. Okay, so in order to activate it for Windows, you do env scripts activate. Okay, you run that. Okay, I press enter and it should run. You can see here it says env. Okay, ignore the base thing. It's a Conda thing. Okay, I can do Conda deactivate. There we go. Yep. So see, it was a Conda thing. Nothing in particular. Okay. You can see a greenish env here. Okay. Now for Mac or Ubuntu users, basically Unix-based users, you have to do source env. I think it's in bin, and then you have to do activate. Yep, there you go. Source bin activate. Yep. It's in bin for Unix based, and for Windows it's in scripts. Okay, with the Unix based systems, you have to use source. Okay, if not, it won't recognize it. Okay, cool, awesome. Thanks for sharing, Tammy. Nice. Okay, so that's it. It's as easy as pip install PyBullet. Was it like that? Yes, there we go. Cool. So let's just wait for pip to do his job. In the meantime, you can't see the stream? You should be able to see the stream. Am I live? Is everything okay? Yeah, maybe refresh your page. Thanks, Tammy. Okay. Poof. Cool. It happened to me. It happens to me all the time when I go into a meeting. I don't unmute by default. Okay? So thanks. So sometimes I think like, hey, I hope that doesn't happen with the stream. Hey, thank you so much. 24 years. I feel like my knees are, I can hear them do weird noises already. And I'm like, no, not me. But yeah, I guess that's something when you get to 24 years old on. Okay, cool. Nice. So, oh, my bad. No, thank you. Cool. Okay. So if you ask yourself, how do I clean my terminal like that? Control L. Okay, I do Control L and that's it. You can do also, I don't know if it works here if you do clear. Yep, there you go. You can type clear or Control L. Okay, I use Control L because it's way easier. It works on Unix too. Okay, cool, nice. So there we go. Should I zoom in? I'll zoom in a little bit there. If you need me to zoom in a little bit more, just let me know, okay? Cool. Easy as import PyBullet as P, okay? Easy. We have to import some data, okay? Import PyBullet data. When you install PyBullet data comes by default, okay? And let's import time. There we go. Cool. So first part is to set up everything. Okay, it's a GUI. Okay, so you can use a user interface. It's good. Okay, we have to set it up. Okay, so to set up. Oh, by the way, before I continue, everything's on my GitHub. Okay, so if you wanna follow along, and then you're gonna use the code for something else, then give me a minute. It's here, and then open source. There we go. Cool. So, oh, my bad. There you go. So you can find all of the codes that I'm going to use here, labeled with the same title. Okay, PyBullet 1, 2, and 3. Okay, cool. So the setup. Okay, so p.connect. Now we have to connect with the GUI. Okay, what does this mean? It means I want to connect with a user interface. There is an option for not connecting. Okay, using the user interface uses your computer's resources for it to look pretty. Okay, if you're training something like reinforcement learning, don't use the GUI because it'll take more resources. Okay, they're training, you don't need to see them. It's better if you check the metrics in the terminal rather than the GUI. Okay, cool, nice. So we need to connect PyBullet information, URDFs, default robots that are preloaded to PyBullet. Okay, so what we do is p.set additional search path. Okay, and then what we do is PyBullet data.get data path. Okay, something I don't understand about people when they're working with Python is why use camel case? I don't know. I don't know if it's so beautiful when you use like an underscore. I know that this is called kebab case. Okay, it's because it's like a kebab, and this is like a camel, you know, up and down, up and I don't know. That's how I learned it. But yeah, I don't know why it's beautiful with underscores, and then you get all JavaScripty with this. I don't know. I don't know. Okay, cool. Now we're connecting the data, which we'll use in a second, and everything will be better. But you can find lots of robotic data here that are preloaded. Okay, if you want to create your own robot, you don't use this. Okay, but in our case, we'll create or we'll use a robot that's pre-created. Okay, cool. Now we have to do. We reset the simulation so everything loads. Okay. Parent is already in underscore. Yeah. Why not keeping the same like nomenclature, right? Like I get it for classes. So if you want to name classes, I do use camel case. I think that's the only thing. For methods, nah, it doesn't look good. I don't know. I feel doesn't feel good. Okay, so reset simulation. Cool. Okay, now with the simulator, we can set the gravity. Okay, so set p dot set gravity. Okay, careful here. Okay, 0, 0 minus 9.81. What's going on? Oh, wait a minute. What? If you want logic, best not ask the Python people. Yeah, no. Win some hacks. What is your main programming language? All line, no spaces. No, thank you. That's horrible. Okay, that's the worst thing that you can do. If someone is okay, I'll say it. Okay, if your company is going to, you know that you're going to get laid off, that's what you can do. Yeah, don't do it. Okay, cool. Writing in C. That's how I started with C too. Like I started learning C, then went to C++, and then Python. I get the camel case, but when I started using the underscores, it just everything went better. Like, it's just I don't know. I feel like when I don't know if you've seen the transition between color TV and black and white TV. That's how I feel like when I started to use underscores. Okay, cool. Okay, so with gravity, and I'll add the comment here: X, Y, and Z. Okay, remember we have the fingers. Okay, we know that Z either goes up or down. Okay, if it's 9.81, then it goes up. It has to go. Something has to go down, like right. That's gravity. So minus 9.81 meters per second is the gravity. Okay, so it goes down. Okay, in Z. If you put it in Y, robot will just go flying. Okay, cool, nice. So that's the setup. Okay, you can set up lots of different planes. You can do your own. There are some pre-defined planes. We're going to use for this first one the usual plane. Okay, so you do set up the plane. So plane equals p dot load urdf, and then you do plane dot urdf. Okay, hold on. Where is this? Like, do I have this in my folder? Nope. This was loaded here. Okay, so if you have your own additional paths, you should add them like this. Okay, in this case, we're using PyBullet's predefined paths, so we have some URDFs here that we can use by default. Okay, cool. Now, we're going to load a Kuka Iowa arm. Is that how it's pronounced? I'm not sure. Load the Kuka IIWA arm. Okay. You're 30. Well, that's good. Who says you're old? Just you. I'm 24 and I'm saying I'm old. Like, yeah. I'll be 60 and I'll say that I'm old. But if I were to be 59 when I'm 60, I wouldn't feel old at all. Like I look at my brother, he's like 16, and I feel like sometimes he looks like a baby, and I'm like, I didn't look like that. I probably did. Okay. So we do the KUKA equals p dot load URDF. Okay, same thing. It's in KUKA IIWA. What the hell? There we go. And then what's wrong with my typing? Model.urdf. Okay, there we go. Now, we have to specify the coordinates where we want it. 0, 0, 0 sounds good. Okay, we don't need it to be in a specific coordinate. In the middle is fine. Okay, and use fixed base equals true. Okay, why is this? Because this is not a moving robot. Okay, it's an arm. It wouldn't be good if it moves. Okay, no, that doesn't happen. Okay, cool. Okay, now we have the plane and we have a robot. Very simple. Okay, so this robot, this is how it looks. So let's just Google it real quick and see what we're working with. KUKA IIWA. There we go. That's the one. Okay. So, looking at this brings back old memories. Okay, you can see it has 1, 2, 3, 4, 5, 6, 7 degrees of freedom. Okay, it means we have 7 joints. Okay, now this is how you do the math. Okay, it's called inverse kinematics. Okay, and then you can predict points based on weird things. Okay, but we're not going to dive into that today. Okay, this is the KUKA. Okay, should look the same in the PyBullet. Okay, regarding the PyBullet libraries, what do you do if it's stuck at building wheel for PyBullet? Ooh, try Control C. So stop the building and try it again. Let's see if that works. I think it may be either an internet issue or a wheel in Python is broken. So just probably my first question would be, are you sure you're in the virtual environment? Sometimes, what's kind of slow? Oh, maybe I had it cached. I'm not sure. Did I have it cached? Can I see it? I can't see it. But yeah, it took a while. Okay, it probably takes a while. So leave it there for 5 more minutes. If not, Control C and try it again. Everything that's downloaded should be cached already, and it should go pretty fast as to the point that you're in right now. Oh, it's Python 3. It's not Python 2. Okay. Cool. So let's see. Control params. Okay. I'm talking too much. Let's just do it real quick. Joint indices equals a list of range 7. There we go. Okay, so it's 7 different joints. Okay, so we need a list of 7. Okay, so we can control each and every single one independently. Okay, cool. Now joint velocity equals 0.02. Now this is decent. Okay, you can play with this, but yeah. Okay, cool. So let's learn how to control this for the user. Okay, let's print. Can I do this? Yeah. Okay. Let's print this. So control the robot using. We can do P or U for joint. Let's do J0 for joint 0. Okay. Up, down. Okay. Cool. Now let me just do this. Now the next one will be O/I. Same thing. Instead of this, it's joint 1. Okay. Now, Okay. Yes, I am in my VNV, and pip works fine. Otherwise, I tried it again. It seems stuck and have my version by the real. Yeah. Leave the wheel building. Maybe it's taking more time because of I don't know how many libraries you have installed in your root Python. Okay. You can text me um on Discord, okay? Just let me know and I can help you there, okay? You can share me some screenshots and I'll try to help you debug, okay? Cool. So the code's in my GitHub, so you can use them as long as you want, okay? Cool. So T or Y for joint 2, and then R or E for this takes a lot of time to write, I know, but if not, then we won't know how to control it. L for K, awesome, you're welcome. For joint 4, that's funny. J or H for joint 5. G or F for joint 6, and last join. Oh, no, that's the last join, okay? Or Q for quit. Okay, awesome. Now, printing that for the user, and then this simulation has to be forever, okay? So, joint pause equals, actually, let's initial joint angles. Okay, now joint pause equals should be 0 times 7. Okay, and now we want this robot to start like this. I think this is pose 0. Okay, where all of the motors are in position 0 or 0 degrees. Okay, it could probably look like this or like this. Okay, cool, nice. So let's open this. Okay, so setting the initial position to 0, and then while true. Okay, now first thing is key. Let's read our keyboard. So keys equals p dot get keyboard events. There you go. Now let's get the Q for quitting. Okay, so we get the value of Q in keys and keys or Q. Okay, and where's the and? Where's the and sign? Okay, there we go. And the and sign P did key was triggered. Okay, all of this just to stop. Triggered. Yep. Break. Okay. So basically, if we press Q, then the event should be called and we break. Okay. So bye-bye simulation. Okay. Cool. Now, real business. Okay. If OR, okay, this is a lot to type. I usually don't like to copy paste, so we'll copy paste just this time, okay? Because it's the same thing, but just changing some things, okay? Can I do it with a for loop? Wait a minute. Let me see if I can do it with a for loop, okay? Join position 0, PU. I think I can do it with a, yeah, because this is too much to write. Should I try it? Let's leave it with as it is, and then we can just change it later. Okay, if OR in Q, my bad. Oh, sorry. Q in keys and the keys in, but it's not Q, it's P. So starting with the first one, okay. So OR in P, and This part over here, P key was triggered. Okay, so we're checking logically if this was triggered. Actually, not triggered. Key is down. Okay, so we check. What's wrong? Okay, my bad. Okay, key, blah, blah, blah. Yes, then joint, because in the first one, okay, in 0, let's add some velocity. Okay, so what was the name of the, there we go, joint bell. Okay, so what is this doing? Okay, so if we press P and we keep pre-pressed, then we add a little bit more velocity to our joint. That's basically what robots do, add velocity. Okay, under the hood it's voltage, over the hood it's velocity. Okay, cool. Now let's do the same thing now for U. Okay, so remember P was for up. Probably should have done it all the way around, but okay. So up, U would be for down. Okay, for the first joint. Okay, so instead of increasing the velocity, we decrease velocity. Now it's like, hey Bullet, what happens if it's at 0 velocity? It just goes, instead of going clockwise, it goes counterclockwise. Okay, so if you want to stop it, you just have to press one time P, it goes forward, and then you just press one time U, and it cancels out, so it stays there. Make sense? So it's not as stopping as it cancels out. Okay, that's what it does. Okay, cool. Now this is for joint 1. Now let's copy paste the whole both chunks. Instead of P and U, we use O and I. Okay, O and I. Careful, remember it's 2 times. Okay, now it's not joint position 0, it's 1. Okay, so it's like your elbow. Okay, so this is, let's do 1, 2, 3, and then 4, and then 5. Okay, so if I'm just moving the first one, I would go like this. It's a cool thing that I can do. See that? Woo. So yeah. Okay. Joint 1 would be probably my wrist. Okay, so I can do this. Okay, so my finger can be stuck like this and moving like this. Okay, cool. Now, same thing for the second joint, which is with T and Y. T, oh, my bad. T and Y. Instead of 0, it's 2. Now let's do a little bit faster because we're running out of time. There you go. TY, and then same thing for R and E. Remember to change it twice. Same thing for R and E. That's why I said we can do a for loop, add more logic to it so it's prettier. Someone said Python users don't know what pretty is. So let's leave it like that. Okay. Do the same thing for R and E, and then should be L and K. L and K. Number 4 should be here. There we go. 5, it's J and H. J and H. I hope that doesn't sound that bad. A truck is just passing by. I'm sorry. 5 and 5. Last one, it should be G and F. My girlfriend, yeah, G and F. And then it's 6 and 6. So far, so good. Okay, same thing for each joint. Okay, the thing that changes is your character. Okay, yeah, cool. Okay, so now we know what the positions are. We haven't said or told PyBullet, hey, I want you to change your positions. Okay, so let's do that. Okay, for I in joint index, I'm sorry, in enumerate. If you don't know what enumerate does, if you have like you have a list like, I don't know, A, B, and C, then enumerate will give you the first variable. In this case, I would be 0 all the way up to 2. and joint index would be A all the way up to C. Okay, so it enumerates and gives you the values, so you don't have to count outside of the for loop. Okay, it's easier. Enumerate joint indices. Okay, cool. Now p dot set joint motor control 2. What does a 2 mean? It's a 2D. Okay, let's do that. Okay, first one is body index equals KUKA. Okay, so we're setting it to our KUKA robot, which is this thing over here. Okay, so it's a URDF. Okay, now second part says joint index. Well, that equals, well, our joint index, right? Right? This joint index. Okay, so we know which joint we're talking about. Third thing is control mode equals p dot position control. Now I'm just guessing. We can do velocity control, angular control. Okay, we're using the position control in this case. Okay, cool. Now target position. Oh, my bad. This is not with an underscore. Okay, this is I, like this. Okay, it's camel case. Target position equals joint positions in I. Okay, I think I did joint pause. Yeah. And then let's add some force to it, right? Force equals 500 newtons, I guess. Yep, there we go. Now, outside of the for loop, two more things to do. P dot step simulation. Okay, it goes step by step. And when you're simulating stuff like this, it cannot, or you cannot ignore sleeping. Okay, you have to let your CPU breathe a little bit, because your CPU will be way faster than you in the simulation. Okay, so it kind of looks weird. Sometimes it'll lag because you can press a button or a key, it won't show up. Okay, so let's do time. Let's sleep. Yes. Let's add some delay of 200 hertz. Okay, 240 hertz. It's fine. It's okay. It's okay. It's okay. It's okay. Cool. Now, as simple as running a Python program. 3, 2, 1. Give me errors. Oh, we don't have errors. Okay. Can you see this? Oh, there we go. Okay, let's leave it there. Okay. So you can see if I scroll up or down, I can zoom in. Okay. You see there's light. I think it's with E. No, it's with C, E. There we go. With S, you can turn off the light. Okay. Turning on, off, off. Okay. Cool. Now you can see position 0 was the one that we predicted, which is this one. Okay. This is position 0. Okay. So whenever you want to start a project, robot has to go to position 0. Why is that? Because you don't want to miscalculate your angles with your positions. Okay, so if you expect 90 degrees of position and you got 0 degrees, and then you say, hey, move 40 degrees, you're way off than where you should be. Okay, it can cause lots of problems. In a simulation, it's fine. In real life, if your robot is, I don't know, building a house, no can do. Okay, cool, nice. So we can move it. It says P or U for the 0 joint, which is this one. Move left to right. Okay, see that? U or P? Is it P? Oh, it was I? Wait a minute, what? P. Huh, why not? Okay, wait a minute. So I goes I and U. Okay, and then let's fix the P just a second. Let's see if everything works. See that? Every single joint moves on its own. Okay, R, E, L K, okay, G F, okay, G is not used. F, can we use F? Yeah, you can see it. You can probably see it, but if I zoom in a little bit, can I get a pair of pamps? No. You can see that this turns. Okay, can you see it turn? I'm not sure. That turns clockwise. Okay. If I do G, so if I keep G pressed, it turns, but I can see that G also takes care of the whole thing. So let's fix that. Okay, we can change the keys and it's fine. So let's go to Visual Studio Code. P and G were not the good ones. Okay, so instead of P, and I tried this before, let's do, I don't know, Z. And instead of G, let's do X. Okay, now that should work. Run it again. So S for deactivating the light. Z, oh, my bad. My bad. I said Z. What? Oh, my bad, my bad. It should be Z and Z. Ooh. Okay, so it should be X and X. Yep, that's fine. Oops, oops, oops. Okay, let's try it one more time. Cool. So zoom in a little bit more so we can see it. Z turns. Is it clockwise? No, it's U counterclockwise. Okay, Z, U. And then I think it was X, the one that turns this one over here. Can I zoom in here, please? Can you see it turn? You can see like the white lines turning, but yeah, that's how you do it, okay? So this is a robotic arm not created by us, but by KUKA, okay? We're using it thanks to this library over here that the devs did for us, okay? Does that mean we cannot create our own robot? Wrong, we can. Let's do something like that, okay? So let me just change it to PyBullet number 2. Okay, there we go, cool. PyBullet 2.py. So I think this is cache. Okay, so for each and every single one of your movements, okay, it kind of keeps them here. Okay, so if you want a log, or you can also graph, which is really good, then you can see it thanks to this. Okay, in this case, we're not going to use them, so outside. Okay, yeah, thank you. Cool. Okay, so same things. Import PyBullet SP, import PyBullet data, import time, import math. Okay, we're going to use a little bit more math. Okay, no worries, I'll explain everything. So same thing, the setup. What was it in the last one? I'm not sure. CID equals p.connect, and again it's p.GUI. Okay, because we want to use a GUI. Okay. Next one is we want to access the whole URDFs again. So let's do p.set additional search path. Okay. It should be PyBullet data .get data path. There we go. Cool. Now, again, setting gravity. So p.set gravity. There we go. Should be 0, 0, and then minus 9.81. Okay. Now you'll have your robots floating. Okay. Cool. That's that. Now we have to set a time step. Okay. In this case, we'll call it dt. Okay, or differential of t. Okay. Should be 1/240 dot. Okay, if you do dot, then it's a float. Okay, let's keep it as a float for now. Okay, and p.set time step. Okay, dt. Okay, cool. Now, we can do plane. Okay, so get the plane. So plane equals, by the way, the plane was, this is the plane. Okay, this chessboard thing, that's the plane. Okay, you can change it to whatever you want. You have to do the URDF by yourself. Okay, but this is a usual plane. Okay, cool. Hello. Nice. Okay. So by the way, who was it? Was it you, Uriel? Did it work or still not working? Or you just stopped it? Just curious. Okay, plane equals p dot load URDF, and again, it's plane dot UR. There you go. Now, we are going to move a robot over the plane. Okay, if you don't add this, the plane will act as ice. Okay, basically it doesn't have friction. Okay, that's not good. That's not real. Okay, you need friction so you can test how it stops, how it actually moves, how it turns. Okay, so we have to set that. Okay, p dot change dynamics. Okay, what do we want to change? Oh, the plane. Okay, -1, it's the base link. Okay, meaning in the first robot, in the KUKA, our base link is this part over here, the black part here. Okay, this one is our base. Okay, for the plane, for a URDF, the whole plane is the base. Okay, so that's what we are trying to set here. It's in the base, okay, of the plane. I want lateral friction equals to 1.0. Okay, usual friction that we're used to here on Earth. Okay, cool. A lot of water there. Nice. Okay, so remember when I said here, this, oh my bad, this here is not the URDF by itself. Okay, URDFs is just a box. Okay, you can actually see it. Let's see it. URDF. You can see that this is a URDF. This is how it looks. Okay, it's a box with a cylinder, and that's it. Okay, this is a robotic arm. As for URDFs, okay, you kinda can paste an image over it so it can look like this. Okay, that's the difference between the visual part and the physical part. Okay, the visual is just visual. Physical is the thing that has the hitbox. Okay, remember that. Okay, so let me just get rid of this. There we go. We have to define. We're going to define an object in the middle. Okay, so wall collision with double L equals p dot create. What's happening? Create collision shape. Okay, so we are creating the hitbox of something. We don't know what. Okay. Okay, it says, what is the most important part, position or angle? Position or angle. What do you mean by that? So you have to track. So if you want to track the position, you have to track the angle. Okay, everything's at angle. If it's a, for example, if your motor, it's like at, I don't know, 10 degrees, then you know it's like slightly to the left side. Okay, oh, sorry, to the right side. If it's like 90 degrees, it's like all the way up, so on. Okay, angle I think is the most important one because it's the one that you can do math with. The position is just place in space. Okay, cool. You sound like you've written prototypes for Mars rovers. I haven't. I would like someday. I have done some prototypes way not way, but like like a year ago, I did a prototype. A complete disaster. Okay, that was horrible. But it kind of worked. So yeah, the project was a rover that planted trees. It had a drill. It drilled the ground and then planted it. It wasn't a tree. It was a well, the idea was a tree, but we couldn't do a tree because it was too heavy. So we had to do the seeds. Okay, so it planted a seedling, and with a special like the seed was covered by something that helped the seed. Okay, moon trees, that would be cool. No, it's like it was just like seeds or seedlings, and then it just dropped the seed there, and then it covered it with the dirt that it kind of, you know, moved. So yeah, everything was done with ROS, which is a robotics operating system, with an Arduino, a Raspberry Pi. Yeah, it was fun. It was fun. Okay, so a geometry box. Okay, half a bent extends equals 1.0. I'll explain this in a second. 0.1 and 0.2. Okay, so what this means is we're creating a geometry box. Okay, it was fun. It was fun. And then we burned our H bridge. The H bridge is the one that controls your engines. I didn't want to do some calculations, and I said, yeah, that works. And after like 5 minutes of full throttle, it burned. And by burning, I mean smoke and fire. But yeah, I aced that part, so it's fine. Okay, half extent means in the X value, Y value, and Z value. Okay, how long and width would I will like it to be? Okay, it's 0.1. No. What's wrong with my typing today? It's horrible. Each time I stream, I type horrible. Okay, cool. Let's do find the visuals of the wall. Cool. So we have a wall collision thing. We cannot see it. Okay, so we have to see it. Okay, so let's do that. Oh, by the way, that was a cool one. Yeah, it was a cool. But again, I do prefer drones, so I like working with AI with drones. It's fun. It's cool. Wall visual equals p dot create visual shape. Okay, p dot geom box. Okay, so we're going to create a visual box of extent equals 1.0, 0.1, and 0.2. If you ask yourself, hey, any funny story with GBA color, any funny story with drones? Yep. What friend? So we lost control of that drone, and one of my friends had the dumbest idea ever. He put his hand like up in the drone, and one of the like the things that turn sliced part of his finger out. Yeah, not good. 001. Why it happened, I'm not sure. Okay, I'm not sure why that happened. We just lost control of the drone. It was in auto mode. Hey, and then we reverted back to manual mode, and drone was like, no, won't do it. And yeah, we had to sacrifice the finger there. But I was going to throw my jacket, but he didn't want to. So yeah, he'll remember that for the rest of his life. Cool. Okay, so we created a visual. Okay, with the same parameters of the collision. It's a geometry box. It has color. Okay, it's going to be red. Now we're going to have to merge both of them. Okay, so wall equals p dot create multi-body. Okay, it feels like if you have used Unity, it feels like Unity. Okay, so base mass equals 0.0. We don't want it to have mass. We don't care about it. Okay, base collision shape index, meaning what is the collision thing? Okay. Okay, wait a minute. Let me just finish this and I'll get to your comment. Wall collision. Base visual shape index equals wall visual. Basically, you're saying the collision thing, it's this part, the visual part is this, okay? And base position equals 1.0 in X, 0.0 in Y, and 0.2 in Z. Now, why? Okay, why add the 0.2 in Z? Because you want it over it, not like you don't want to have some pixels that are in the middle of the plane. Okay, because the plane has thickness. Okay, so to prevent that, you just do it 0.2. In the end, if it's too tall, it's going to fall. Okay, it's fine. Okay, here we have, sorry, I confused moon trees. Moon trees are a thing, though. Have you done any research on drones entering orbital trajectories from the troposphere out? Nope, that's going to be cool. That's it. That has to be like a, instead of a your usual, it could be like, I don't know, the DJI drone that you use. It has to have a very, very, very powerful engine. It's interesting. I love the idea of drones in space. I haven't done any research. Like, if you have and you have cool pages, send them. And yep, it's really cool though. And what's a moon tree? I hope it's not something weird. Moon tree. Oh, cool. It's like, okay. What? Trees growing from sitting in a jar to the moon. Initially, oh, this is a thing. Okay, it's not a tree by itself. It's like seeds taken to the moon and back. Wow. That's cool. That's cool. That could be awesome. I don't know. Starting a new company with drones, that could be cool. Okay, nice. So we have a wall. Now, let's add some dynamics to the wall real quick. So p.change dynamics. We add it to the wall. -1 means the base. Okay, we just have one link for the wall. It's that link, okay? And then lateral friction equals 1.0. Okay, why is that? Because if not, if the robot slams into the wall will just, slide forever. Because if we don't add friction to it, then it won't have any friction. Okay, cool, nice. So that's a wall. Let's kind of take a look at that. So can I just skip that? Okay, no, let's just leave it as it is then. We'll just create a robot then. Create robot, okay? For whoever wanted to create a robot, this is how you do it, okay? So let's speed things out. It's going to be a robot like this one, okay? Like this one, okay? It's basically a cylinder of some radius and some height, okay? So we can do radius. Radius equals 0.2, so it's not that big, okay? Height equals 0.22, so it's I liked it, okay, when I tried it. Cool. Okay, again, we have two parts of this, the collision and the visual. So let's start with collision, okay? Base collision equals p.create collision shape, okay? Now, we wanted a box first. Now, we want a geometric cylinder. Okay, radius equals radius, okay? height equals height. Was that spelled correctly? Cool. Okay, so the collision of a geometric cylinder with radius 0.2, height 0.2. Okay, easy peasy. Okay, next thing is base visual equals p create visual shape should be a geom cylinder. Okay, same thing. Radius equals radius. Length height. Okay, I'll get to that in a second. And RGBA color with capital C equals 0, 0, 1. Oh, how about 1, 1. Okay. If you want to ask, why do you type that bad? This is not my usual keyboard. Okay, this is a new one. I got it like 2 or 3 months ago, so it's not that new. But I was used to, I think it was blue keycaps, like the blue switches, and this is red. So if you barely touch it, like the keycaps, it reads the signal. Okay, so I have to get used to this. Nice, yes, always nice. Okay, cool. Okay, now like this, like a wall, you have to build a robot. Okay, robot equals p dot same thing, create. My bad, multi body. Okay, I'm sorry. Typing is not on my side today. Base mass equals 1.0. This is in kilograms. Okay, so this mass over here, it doesn't weigh at all. Okay, like we won't move the wall, so it's fine. Okay, if you want to calculate more in-depth stuff about your robot based on voltage, speed, then you have to accurately use the mass. Okay, cool. Now, base collision shape index equals our base collision. There we go. I copy pasted, no issues there. Base visual shape index equals base visual, and base position equals 0.0, 0.0, and careful here, 0.5 times height. Now, let me get back to this, okay? For PyBullet, in a visual shape, the length should be the height. Okay, it creates instead of creating him like this, it creates him like this. Okay, so that's why the length is the height in this case. Okay, now what about this? Okay, now the center point of the robot is in the center. If you don't do this, your robot will be in the middle of the plane. Okay, we have to up it up. That's why we do 0.5 times height. Okay, cool, awesome. Now p dot change dynamics. Okay, robot has mass, collision, visual. We have a position for it. It's in 0x, 0y, 0.5 times the height in z. It's not fully body functional physics world. Let's add that. Okay, so what do we want to change the dynamics of robot? Okay, in the base link, because we just have one link. Okay, so it's in the base link. Linear damping equals 0.04. What is linear damping? It reduces linear velocity, as if you were in the real world and you'd had wind, air, I don't know, water. Okay, That's the linear damping. Okay. Now, angular damping equals 0.04. It reduces the rotational velocity, same thing as if it were in the real life. Air, moisture, water. Okay, if it's on the water, then water. Stuff like that. Okay. And lateral friction equals 1.2. It's the one. The more lateral friction you have, the less sliding the robot does. Okay, so you can add 1 to follow this one over here with the plane. Okay, let's just add a little bit more friction to it, following the mass. Okay, why not? Okay, cool. Now, control. Okay, let's control this thing. Okay, now, velocity equals 1.0 and turn speed equals 1.5. Okay, careful. If you remember, we're not turning in X. Okay, so we're not turning in rolling. We're not pitching. Okay, it's not in the Y, but in the Z. We're yawing. It sounds weird, I know. We're yawing. Okay, so this controls the yaw speed. Okay, Z angle speed. Okay, cool. Now, print to the user. Okay, use the arrows to move the robot. Happy face, as always. Cool. So, why using the try block? Just in case. Okay. While true, then we can do the same thing. Keys equals p.get keyboard events. Okay. Now let's. I don't want to type it. Let's do it from here. There we go. This part over here. Careful with indentation. There we go. Now, linear equals 0. Okay. Okay. Now, would you program this as a centrifuge, or do you account for centripetal force? So give me an example. So what is it that we can program, or what should I like? Give me an example, because I'm not sure in a simulation. Why would you add centripetal force? Because it just if you're talking about the damping part over here, if you don't add the damping part, then you have centripetal force, which never stops. Okay, you just keep spinning all the way around. Okay, like a merry-go-round. Would be centrifugal. What's a merry-go? Is it what I think it is? Wait a minute. My English. Merry-go-round. Is it this? Let's see. Okay. Yeah. Got it. So, would be centrifugal. Yeah. So centripetal is, instead of in yaw, it would be in your either X or Y. Never. Okay. Now, in robots, you always use the centrifugal, or in this case, it's like the Z value of it for turning. Okay. Just a little bit of FYI. If you see this, you can see that each joint is located, every single part of it is in Z. Okay, so you can see this is Z2, and then it goes up, it says Y, but every single calculation, it's made in Z. Okay, so you start like this, okay, where Z looks up. Okay, so that's your first joint. Second joint, you have to tilt 90 degrees in X for you to get the Z in 90 degrees. Okay, and then you program everything based on Z. Okay, never with X, never with Y. Okay, always in Z. So it's always in the yaw part moving. Okay, so whenever you're programming a robot, never use would be the centripetal force, always the centrifugal force. Okay, so that's why I don't remember mathematically why. Let's see if I can find it real quick. Let's see if I can find. There we go. Okay, you can see it here. Maybe not. Okay, this is a real quick thingy. Yeah, okay. Yeah, you get the Z there. Two linear robot. Let me find the equations real quick. There it is. This is the, yep, this is it. Okay, cool. Uh-huh. There we go. So you can see, yeah, okay. So you can see that in this part over here, the only part that we actually use and doesn't, how can I explain it? Okay. I'm new to this. It's fine, okay? Let me just think about it in an easy way to explain it, because not math. Here, maybe this one will help. How can I do this? How can I explain it to you? Okay, you never do it because of these formulas right here. You don't use your X or Y value because you get into problems when you're doing sine or cosine. Okay, so it can give you either 0, and sometimes you'll divide over that. I think we saw one of these here. You can do this, and if one of these two is 0, everything's messed up. Okay, so you have to use Z. Okay, yeah, exactly, basically. Okay, so never use X or Y. Okay, some people use them, but it's not inverse kinematics. Okay, so as a convention, always use Z. Okay, cool. So I hope I explained it without without doing a lot of a mess here. But yeah, that's basically what you have to always use. Should be the centripetal, is it? Now the centrifugal force. Okay. Basically in Z. Okay, cool. Nice. So linear, and we have angular velocity equals 0.0. Okay. If these dot get, okay, let's see if we pressed once. Okay, let me just scroll down a bit. There we go. Did I update this code? I think I'm going to go into a problem here. I hope not. B3G arrow, okay, and 0. Bear with me. And now this AND, this is a logic AND. This is not like a comparison AND, this is a logic AND, okay? And P dot key is down, okay? Then linear equals velocity. What happened here? We're checking if our arrow up is being pressed, and the arrow is being pressed, basically, okay? So our linear velocity becomes our velocity, okay? Let's do the same thing for, oops, there we go. Instead of up, going down. Okay. Then linear goes minus velocity. It's not that it stops. It just adds inverted velocity. Okay, means it doesn't add plus 12 volts, but minus 12 volts. So the motor or the engine would go, instead of going to the left, goes to the right. Okay, cool. Now same thing for should be left arrow. Okay, then in this part is the angular velocity would become, I think we said turn speed, and it's not angulate, it's angular. And if keys B should be right, linear angular becomes your minus turn speed. Okay, there we go. Cool. Okay, so read the current yaw, okay, to convert body forward to world velocity. Okay, so we have to transform it to see it. Okay, so we don't care about the first one, but the second one equals p dot get base. Come on, base position and orient. See, it's horrible when you do camel case. It's just horrible. Okay, whoever loves camel case, seek help. Okay, underscore underscore and then yaw equals p dot get Euler from quaternion. Okay, I'll explain what a quaternion is. Okay, so we get the base position. It's in, as far as I'm understanding, okay, again, is this base position, it's your x and y value. From that x and y, you can get a quaternion, which is roll, pitch, and yaw. Okay, so we got the yaw from the Euler quaternion, and then we can use that yaw to adjust the velocity. Okay, so Vx equals linear times math.cos. I'll explain this in a second. Yeah. Okay. Now velocity in y equals the same thing, linear times math.sine. Careful there. Of yaw. Okay. Now I'll explain it. Let's just finish the code real quick, and I'll explain it. Okay. Apply vels instead of resetting pose. Okay, so p dot reset base velocity. Okay, we reset the robot. Okay, linear velocity will be changed to velocity in x, velocity in y, 0.0. Okay, y in the z we have a 0 because we're not going up. Okay, in this part over here we change it from roll, pitch, and yaw to xyz velocities. Okay, we're not going up, so there is no velocity up, but we're going left and right. Okay, going in front means going left and right at the same time. Okay, cool. Now, angular velocity equals 0.0, 0.0, and angular. Again, why? Because if we're looking at roll, pitch, yaw, okay, or xyz, the only one that turns is z, not x, not y. Okay, if not, the new robot will be doing this, which is not true. It cannot do that. Okay, cool. Okay, let's just finish this by repeated step simulation. Okay, a little bit of time. Let's leave here the key. And then add the finally here, which is here, p the disconnect. Cool. Water. Nice. Second thing. What the heck just happened? Okay, what was that? Okay, cool. Let's go back here. Okay. Remember what we did in PyBullet 1, which was pressing keys. From the keys, I can get, in this case, the joint position to add a little bit more velocity to it. Okay, it means, Mr. Engine, please start turning. Okay, it means Mr. Battery, please give me some voltage to give it to Mr. Engine. Okay. Same thing. If I'm getting the up arrow and the key is down, okay, then linear velocity gets velocity. Okay. This velocity here, remember we said, hey, we want to have, I think it's 1 meter per second of velocity per engine. Okay. So we're saying, hey, go have a linear velocity positive forward, backwards, left, and right. Okay, what does this mean in the real world? It means if I have two engines, if I'm going in front, both of my engines have the same velocity. It means it has the same voltage. Okay, now careful. That's why I burned my H-bridge. If you don't adapt the voltage inwards and outwards, the torque will burn H-bridges. Okay, so you have to have a either very powerful H-bridge, or you have to be careful with the torque. Okay, it depends on if you change the H-bridge or your engine. Okay, both of them should work. Cool. Okay, now we get the position and orientation. Okay, position and orientation. From this XYZ, we get a quaternion from Euler, roll, pitch, and yaw. Okay, from there, we can get X velocity, Y velocity, and we have our angular velocity. Okay, now, Y cosine and Y sine. Every time you have to work with X, every time you have to do math for the X plane, it's not X plane, it's the X plane, okay? Then you use cosine, okay? If you do it with Y, you use the sine, okay? Let me just real quick, see if it's because I think, calculator, there we go. We can do this. If we do, what happens if you do, for example, sine, where's the sine? Oh, there you go. Sine of 0 is 0. Okay. Now, sine of 90 should be 1. There you go. See? So, for us not to get in problems with calculating in Y plane, we use sine. So we don't get 0. Same thing for cosine. Okay. If you do cosine of 90, you'll get 0. Okay, it means in your Z plane, in your Y plane, cosine doesn't work. If you use cosine in Y, you'll have some divisions over 0, and you don't want that. Okay, so that's why it happens. Okay, cool. That's why we use, again, always, and that goes for everything that has to do with physics. X cos, Y sine. Okay, easy peasy. Okay, cool. Now let's see if this works. I don't think it'll work. I think I have an error there. Let's see. Yep. What does it say? Okay, get data path. Get data path. Oh, it's lowercase g. Don't run from errors. Okay, when you get errors, try to understand what they say before going into, I don't know, ChatGPT or something, okay? Why is that? Because it's a skill, okay? Don't go and ask ChatGPT about everything if you have an error, because, you know, it's just as easy and it won't work for you, okay? Cool. Now, get data path. Got an argument, but has to be string. Okay, what did I do wrong? Is it because this has to be like this? Maybe? Yep. Now, next one. Base position equals this. Base position, camel case, my bad. Oh, here it is. See that? Base position. There we go. Cool. Let's run it again. See how it looks. Again, create multi-body, Create multi, capital C, my bad. Create multi-body. It's this one. Is it the only one? Create multi-body, yes. That should be it, hopefully. Another error. Why me? Okay, did you mean, yeah, I meant get Euler from quaternion, Mr. U there, my bad. Quaternion, yes. Fourth, nope. This is embarrassing. Step simulation, careful there. Careful with my step simulation. Where is it? Step simulation. There we go. I definitely should have not gotten this keyboard. It's just there we go. Cool. Awesome. So this is how it looks. Okay. Now G to get rid of everything. Okay. Now you can see here we have a box. This box is 1. Okay. So we can see that each box or each square is 50 centimeters squared. Okay. So it's 50 centimeters and 50 is 1 meter. I think it was 0.2 times 0.8, something like that. That's the box. Okay, now, if you use the arrows, you can see it moving, okay? See that? Moves. Okay. Now, this is an issue. Oh, no, that's fine. Cool. See that? So, you can use it like this, and what happens if we collide? I cannot move this. Okay, see that? See that? Why? Because this has a lot of friction. Even though it doesn't have mass, it has a lot of friction, and I think we added something called did we add it? I think we didn't add. Okay, no. Because in this part over here, in this robot, there was a joint which was that doesn't move. Was it here? Oh yeah, here it is. Use fixed base. But in this case, we didn't use it, but we have where's the body? There we go. We have lateral friction of 1. This robot doesn't have enough speed. Okay, what happens if we do 10 of speed? Let's see what happens. Okay, so Q for this, do this. Let's see if we can move the box. I'm not sure. I don't think so, but let's see. Ooh. Yep, no, we can't. No, we can't move it. Okay, because it doesn't have it has a lot of friction. Okay, compared to the ground. Okay, cool. Now, let's see if we can do PyBullet 3. Okay, now PyBullet 3 is okay. That's going to take some time. Okay. Cool. This is what I usually do when I run out of time. I will copy my code, paste it, and explain it. Okay, you can find this in my GitHub. Okay. Control C, you'll be able to see it here. PyBullet 3.py. There you go. So get rid of these two. There we go. Nice. So 120, 30-ish lines of code. Cool. So we know about this. Okay. So we connect the GUI. We do the data path. Okay. This part over here is for the camera to follow the robot. Okay, so what we're saying is we wanted to keep a distance of 2. We wanted to turn in yaw and turn in pitch. Okay, and our target position, the first one is 0, 0, 0, which is in the center. Okay, now add the gravity, add the delta time, which is our steps. Okay, which is 240 hertz. Okay, now we load the plane as we used to do it. The dynamics would be the same of the plane. In the base link, we had friction of 1. Okay. Now, we have either here random walls or a maze. Okay, we can use both. Okay, let's just add random walls first. So it's a function that adds walls of n walls. Okay, and for if you see an underscore like this, it means we don't care about that that variable. Okay, so I don't care for, I just want to loop for the number of walls and basically do the collision, the visual, and create a multi-body of walls. Okay, so far so good. In the maze, we can do the same thing, but for each one, we can have a multi-body. Okay, if the cell is 1, if it's 0, then nothing. Okay, cool. Now, I created a maze, but we can create the walls too. We'll do that in a second. The simple cylinder robot, radius of 0.15 and height of 0.1. Okay, now collision and visual shape should be the same as last one. You can see the RGBA color is red. Okay, robot, we created robot using the create multi-body. Okay, we change the dynamics of the robot. Its base link to have 1.2 friction. Okay, velocity and turn speed, we know what they are. Now, what is this? Okay, remember I said you can use some sensors. Okay, a ray sensor is a lighter. Okay, so or like a lighter. Okay, it basically shoots rays and can read from those rays. Okay, if something touches your ray of light or your beam of light, then something's there. Okay, we had a minus 45, 0 and 45 degrees, so it's 3 rays like this. Okay, so it's like this. Yep. We can do an auto mode. It's not really auto. It's just if it finds something in one of the angles, then just turn the other way. Okay. Robot Explorer running. Use M to toggle manual mode. WSD to move manually. Okay. I probably should have changed it to arrows. Okay. Yep. Because WASD doesn't work. Use arrow keys to move manually. Okay, cool. Now, while true, get the events of the keys. You know how it works. If it's Q, we get out of it. If we get M, then auto mode is not auto mode. Okay, how do you do it without if auto mode is true, then false, else true? With this, no. Okay, you just inverse it. Okay, cool. Now, position orientation, we get it by this. XYZ, we get by this. Why is Z not important? This robot cannot fly. Okay, so we don't care about the height. Okay, we don't care about the pitch nor the roll, but we care about the yaw. Okay, which is the Z angular angle. Okay, now linear angular velocities. If we are not in auto mode, we know how it works. If we press it on a key, then we either add or subtract velocity. Same thing for turning speed. I don't know why I put this plus, but turn speed or minus turn speed. Okay. Oh, actually plus. We can do plus equals here. Okay, cool. So if not, then this is the important part. If we are in auto mode, we have to get the distance of everything that I see in front of me. Okay. For each angle deg in sensor angles, it means for each one of these, okay, I want to see, hey, you do some math here. You say, hey, am I turning? And if I'm turning, I want to calculate the degrees. So it's not always 45, because if you turn, if my cup or my mug, this is one ray, okay, for example. If I turn, this thing turns with this, okay? If you don't add this yaw plus math.radians, then this would get stuck looking at in front of it, and this would turn without it turning with it. Okay, makes sense? Now, we can get a position, again, x always cosine, y is always sine, okay? We're adding a position here. We can do We can check the distances. Okay, result 2, if result 0. So this result is I wanted to get from the rays a test from the position to position. Okay, it means, do I have something in front of me to position? Okay, so from position is my x, my y in 0.15, which is the height of the robot. To position is this x plus the sensor length. Okay, so we're adding length to our ray. If we want the ray to be really long, then we just add the sensor length should be bigger. If not, it's smaller. Okay, then we do, hey, I want you to check the rays. If I have something in my hit distances, then I append the result or nothing. Okay, we can change the color of the rays. Okay, add user debug line is for you to see the rays. Okay, we'll see them in a second. It looks green and yellow. What else? We can move the robot here again. If we were talking about x, it's cos. Okay, so we use the linear for it to move either if it's turning or not turning. Okay, this is for camera. For the camera, careful. For the camera, okay, if it follows the distance, we want some offset here behind the robot, okay? And what else? We get the quaternion here, and that's it. We time that sleep here. Basically, the important part is this, okay? Again, we have angles, one for each ray. For each ray, we check, hey, I want to give this ray some length. It's a simulator. You can simulate light. That's why this kind of doesn't make sense. It's like, hey, if it's a ray, then I don't know. This shouldn't make sense. But just imagine that instead of a ray, in real life, you have an ultrasonic sensor. Okay, an ultrasonic sensor looks like this. Sensor, there we go. This thing over here, okay, which works with an Arduino. It's really easy to use. It tells you if something is in front of you and it gives you the distance. Okay, now if it's too far away, this thing doesn't look at anything. Okay, because it uses sound to locate stuff. Okay, so you can simulate the length of that sensor using this. Okay, cool. Now let's see how this works, okay? Will it work? I hope it does. And there it is. Cool. Okay, so you can see the camera is rotating with us, okay? The robot is trying to do its job, okay? If you press M for manual, by the way, this is on my GitHub. It's this one over here. Okay. So, you can see the robot is trying to free itself. Let's press the manual, move the robot on our own. It doesn't, we cannot see it there. You can see it there. Yep, there you go. Cool. So the bad thing about this maze, and I didn't change it, is that it's all closed, okay? So if you do this and then toggle manual, it'll try not to hit something, but it does, okay? So let's, instead of doing the maze, let's do walls, okay? So go up here, and instead of creating maze, just do, what was it? Random walls. And then let's just add 5 walls, okay? Why not? Let's see how this looks. Cool. So here it is, okay? If we put the robot here, it should miss the box, okay? So let's do that. If it goes forward, it will hit the box, okay? If we toggle on manual, it goes forward. You can see here the rays of it. Oh, now it doesn't want to do anything. Great. Wait a minute. You need a little bit of help. There you go. You can see the rays, and then it should not hit the box. Okay, let's try that again. It goes there. If it hits right there, there you go. It should hit. It doesn't do anything. Oh, that's great. Wait a minute. Why? So the rays should tell the robot to turn. Okay, and then it freezes. That's weird. What about here? Let me see if this happens with all of the corners. Yep, it turned. Okay, I think I'm getting it. It's turning. How can I? Interesting. So I think the problem with this is we are trying to turn. Should be here. The rays are okay, but we are trying to turn. Minus turn speed. Ha! Okay. I think turn speed if left. If left is bigger than... I think the error is here. Wait a minute. Turn speed should be greater than left. Okay, yeah, that makes sense. Should I maybe do this? Wait a minute. I think this is the error. Was it an easy miss on my end? The robot is just going forward. See the rays? Can you see them? I can't zoom in, but can you see the rays there? Those green thingies? Okay, cool. Now, let's do this. Okay, it goes forward. Great. This ray in front of it should see the thing. Oh, there we go. Yeah. Why? Okay, let me try to quickly try this, because I don't know if the 0, 1 helps at all. So what's happening is we're trying to turn if something is in front of us, but both rays are saying, hey, something is in front of us. So we don't have a stop. Okay, that's what I think is happening. Wait. Expected 3 got 2, value left, front, right. Oh, it distances, my bad. Should be this one. Head distances. Let's see if we can do it real quick. Yeah, this doesn't make sense at all. Wait a minute. It's at 0 here, but this doesn't make sense at all. Let's do it in 1. Else linear equals Let's see if that works. Okay, 3 more minutes. It's doing something. Okay, it's trying to turn. Let's see what it does. It's as if it's trying to turn left and right at the same time, but I'm not getting why. Okay. Okay, it should turn. See that? I think it's because... Yeah, maybe the rays are too large. Sensor length, where is this? It's here. Can we do 0.5 maybe? Maybe. If not, then I'm not sure. I'll have to update the code. Oh, this is better. I'm not doing anything though. Yeah, there it is. Okay. Let's do manual. Can we put it here? Okay. Let's see if it can fit. It can't. Okay, wait a minute. Again. Let's get more space. What? There we go. That's weird. That's weird. I'm not sure what's happening. last thing that I can try is maybe I change this. I don't think it's this, but just in case it bugs there. I'm not sure. Now it's bugging because of something. I should have probably added some print statements here. Not sure what this is happening, okay? I'll try to have this fixed by the end of this week, okay? If you want to try this code, just let me know on Discord. You can DM me and I'll try to have it fixed, okay? It should be on my repo, okay? I'm not sure what's happening. I think maybe, wait a minute. Am I dumb? Let's do it real quick. cd PyBullet and then PyBullet 3. Do I have the updated version in this part over here? Maybe not, because I don't know if GitHub's version is bugged. So let's do random walls here. Should be the same. Let's do 3 walls. Why not? Okay. Yeah, this is better. Wait a minute. What happens if I do this? Okay, it's turning and then it'll bug. Nope. Yep. I don't know. It's turning and doing weird things. It tries to think. Give it more space. What it does with more space? Nothing. This is just weird, okay? I'll have it for you ready by Friday. Okay, promise. Just check the GitHub and it should be updated there, okay? Cool. Now, what is the next stream? Global Hack Week. I think it's Rosendo's stream. MLH. There we go. We have, it's not here, it's in the schedule. It's day 4. Okay, it's learning about open source part 1. Okay, yes, it's the intro. Thanks, Tammy. By the way, before you go, could you please give me feedback? Okay. It helps me improve in my streams, and let's check out the feedback, okay? So if we go to the feedback, open it, and then look for PyBullet. Here it is. Click on it, and then you can give me feedback, okay? If it's a 1, I'm not taking it personally. It helps me for me to get better, okay? Cool. And last but not least, if you haven't checked in, please do so. Hello. But yeah, that's it. I'll leave it for Rosendo. Thank you so much for watching. And if anything, just let me know on Discord. I'll be streaming tomorrow. And is it Alberto? Oh, Alberto just entered my studio. And I'll stream tomorrow and on Wednesday, okay? Have a nice one, and yeah, hope I see you tomorrow. Bye-bye.